Welcome to 4.2 Exponential Functions. We're going to look a little bit more at graphs and talk about shifting and different kind of aspects there. And then we're going to go through an exponential function model problem. Okay, so you could go ahead and plug these into your calculator and kind of see what's happening. And what you should notice is we graphed this one yesterday in our other notes, in the day 2 notes. So that's our guy in blue, right? So we could go when x is 0, when x is 1, when x is 2, and we can see what's happening. In this part B, if f of x equals 2 to the negative x, well, remember, that's like saying 1/2 raised to the x. So again, if we were to create a table of values and go through, well, when x is 0, we get 1. When x is negative 1, that's where we get y to be 2. And when x is negative 2, we get this. So what we should notice is this is a decreasing function. But what happens in part C, where we have f of x equals 2 to the x minus 1? Well, what we should notice is it's just our blue graph, but we're shifted down 1 unit. So instead of 0, 1, we're now at 0, 0. Instead of 1, 2, we're now at 1, 1. And instead of 2, 4, we're now at 2, 3. So this just shifts it down 1. But look at D. Now that x, it's 2 to the x minus 1, where the minus 1 is in with the power. So what's going to happen here? Well, this is a case where I mentioned if we were to just go ahead and create a table of values, right? So this is part D. I would choose an x value that makes our power 0. So when x minus 1 equals 0, I would get x equals 1. And now I just choose some points that surround it. So 2 and 3, and then 0 and negative 1. And what you'll notice is everything from our blue is just shifting to the right. So when x is 1, we get y to be 0. So now we're at the point 1, 0. When x is 2, we get y to be 1. When x is 3, we get y to be 4. And when x is 0, we get 1/2 and then 1/4. All right, so you're noticing we're just shifting to the right 1 unit here. And then in part E, when we're graphing this, the only difference is it's the opposite of 2 to the x. So what that means is we're going to take the blue graph and then we're going to multiply it by -1, every aspect by -1. So all it does is it reflects across that x-axis. So generally speaking, we can kind of summarize this, okay? If our base is positive, we're going to be increasing. If our base is greater than 1, we're increasing. If our base is less than 1, we're decreasing. Remember, our base will always be positive. Okay? This k value, like in part B, that tells our graph to shift up or down. If k is positive, we shift up. If k is negative, we'll go down. This h value, like in example D here, tells us whether we shift right or left. If h is positive, we shift right. If h is negative, we're going to shift left. And then this a value tells us whether we, I guess you can say open up or open down. It tells us if it's negative, we're going to reflect across that x-axis. We'll get more practice with graphing as well, but this is just a nice little summary to give yourself an idea of it. A very important number that comes up a lot when we're dealing with exponential functions is the number e. So e is actually a number, and it is an irrational number, similar to what pi is, but it represents this number, 2.718, et cetera, et cetera, et cetera. So if we were to graph this, I just created the table here. We can just plot the points, and we can see that it is an exponential growth. It is increasing as x is increasing. All right, so what we're going to do now, though, is we're going to look at a model problem that deals with the number e, and this actually comes from our book, okay? So I'll kind of walk through piece by piece. Don't really pay attention to this piece at the moment. We'll come back to that. So page 357, number 54 in our book. The number of bass in a lake is given by this equation. P of t equals 3600 over 1 plus 7e to the negative 0.05t. all right? So one thing to kind of keep in mind, another way we can write 7 times e to this negative number is 7 times 1 over e to the positive 0.05t. Keep that in mind. Anyways, t is the number of months that have passed since the lake was stocked with bass. So part A says how many bass were in the lake immediately after it was stocked. So this is when t equals 0. So we can go ahead and zoom in, okay? And all we're doing is we're plugging 0 in for t. And when we do that, we can see that this negative 0.05 times 0, well, that means this power goes to 0. So we have e to the 0, and we know anything raised to the 0 is 1. So this just really becomes, our denominator becomes simply 1 plus 7 times 1. Or, in other words, 8. So we get 3,600 over 8, and we get 450 bass in the lake when it was stocked. Go ahead and complete part B. How many bass were in the lake 1 year after the lake was stocked? Round to the nearest bass. Now keep in mind, t represents months, all right? So if it's 1 year, how many months is that? Go ahead, and you probably need a calculator, but figure that out and check back with your answer here. So you should have plugged t equals 12 into our equation, and then when you plug this into your calculator, make sure you put parentheses around the entire denominator. And I ended up getting 743.54, but it did say round to the nearest bass, so that would be rounding up to 744 bass. Okay, this last part here wants to know what will happen to the bass population as t increases without bound, okay? Meaning as time goes on forever. That's what that means. So this is where I want you to kind of take your attention back up here, where we rewrite this e to the negative as 1 over e to the positive. And what this means is as t is getting bigger and bigger and bigger, what is happening to this e to that number? Well, this value here is also getting bigger and bigger and bigger and bigger. So what does that mean? That means we are essentially having 1 over a really big number, right? So 1 over a really, really, really big number, we essentially call 0, okay? So this whole part essentially goes to 0, this piece right here, okay? This piece right here. So then what we actually have in our equation, I'll kind of write that back down by part D. So as t goes to infinity, right? We can kind of say that it's going to infinity. It's getting super duper big. We end up with 3,600 over 1 plus 7 times 0, right? Because this 1 over e to the 0.05t becomes 1 over a really big number, which is just 0. So then as we just simplify this, we end up with 3,600 over 1, because the 7 times 0 goes away. And so therefore, we have our final answer that the population approaches 3,600 bass. So that essentially tells us that's the carrying capacity. It's another word for saying the carrying capacity of that lake. It will never get beyond 3,600 bass in that lake. If you have questions on anything, make sure you ask in class next time we see each other.